Okay, so we did mean to sample last week. We're going to do mean to sample this week also. So the first thing I want to talk about is pooled and not pooled. They refer to it in the book, but we're not going to pool. Okay, so and there's reasons why or why not you would want to pool basically, which is put them together. So you either see combined or pooled. So you'll see like S sub P or you'd see S sub C. I don't like the sub P one, to be honest with you. So we did pool for proportions. We're not going to pool for means because it basically comes down to if you have equal variances, then you want to pool them together. But it's very difficult to verify that the two populations have the same variance. You have to do so an F called an F test, which we'll go through F later on next week. But it's unreliable for this, so typically you stick to the Welch test for T. So if we look back at last week's notes, let me pull those up. Where's last week's notes? Week 2 and app. Okay, so go all the way down to the end. So you notice we did all the two sample stuff last week, but we did each standard deviation and variance separately, right? And we did the Welch formula, which is this big degrees of freedom formula right here, under the assumption that the data was independent, right? So if you look at these formulas versus the formulas in these notes, they look very similar, except these standard deviations right here are pooled, right? And last week, these were not pooled. They were just the 1 and the 2, the different data sets, basically. So if you look at these data sets we did last week, okay, this is people who had the regular bowl, and this is people who had the oversized bowl. They were not the same people, okay? And we just did them separately, right? If you combine them all into one group, right, and then did the standard deviation of the entire group, that would be pooling. We didn't do that though, okay? So again, pooled versus not pooled. Do they have the same standard deviation? I don't know about the bowls of soup. I have no idea, okay? But we didn't pool them together. So basically, when we did the soup one, we did the standard deviation of the soup, small bowl, and regular bowl and the oversized bowl separately, right? We assume they were not pooled. We didn't pool them together, basically. If we did pool them together, we would just take the whole thing as one data set and figure out the standard deviation. Okay. What we are going to do, though, is differentiate between dependent and independent. We are going to do that. We have to do that. Whether it's pooled or not, we don't necessarily have to do it. It doesn't make a large difference anyways. So if we think about the soup one from last week, these are two different groups of people. Okay, they're not the same person. They're independent of each other, right? So whatever this person has for soup has nothing to do with this person having soup in their bowl, right? They're just different amounts. One does not affect the other. They're two different people altogether. Okay, so this week we're going to do the dependent ones. So the example I have here from the book is people who have cell phones and they either do or do not use it in the car. So it's the same person twice. So the first time this person has 604 milliseconds, the second time they have 636 milliseconds of reaction time in the car with while not using a cell phone. Okay, so that is a dependent sample because it's the same people twice and it's dependent on the cell phone use. Okay, and there's a variety of names. They say like matched pair, stuff like that. But okay, so the formula's changed slightly in here. So you'll see D for difference, okay, is what we're going to do here. Okay, so the first thing is, should we treat these samples as independent or dependent? These samples are dependent because they are the same person and the results depend on the cell phone use. Bold. Okay, so let's make sure that they are actually symmetrical. So what I did was I took that data and I put it into a spreadsheet, right? I'm just going to take, I think we just do that. If we do insert, right, and then I think it's the other charts, maybe? Maybe it's statistical. There it is. Is that the box plot? It is the box plot right there. So that one looks pretty symmetrical, right? Other than the outlier you could ignore. It's the same on the left, on the top and the bottom. If I do the other one, right? Insert. So I click the column first. Insert statistical, right? And that one looks symmetrical also, right? So they're both symmetrical, which means they're normal. There's an outlier, but who cares? Is that an outlier? I guess it might be, because that's a little dot out there, so it doesn't matter. Okay, let's just get rid of these for now. Put them down there. Alright, so we verified that they're normal, which that has to be normal for us to do this. Okay, we'll just get rid of them for now. Okay, let's make this a bit bigger. Go back to our sheet here. They appear to be normal. Okay? To be symmetrical. Right? It looks the same on both sides. You can tell by the shape of it. Right? Because if you look at it, right, it's the same on both sides as far as the lengths of the bars, right? The whiskers. Okay, so we're going to do a confidence interval first. So I'm going to go up to here. I'm going to copy the formula because you probably don't know it. Copy. Paste. Okay, so we're going to need a bunch of things here. We're going to need difference. And we're going to need something else here. That's called d minus d hat squared. We'll get back to that in a minute as to what that is. In the meantime, let's bold, fill those in, yellow, and center them. Okay, so the difference is the d here, right? The difference. So equals yes minus no. You can do no minus yes or yes minus no. It doesn't matter as long as you're consistent in the explanation of the outcome. You would just get a flipped confidence interval and just have to modify. You have to be careful with the hypothesis test. It matches up with what you're saying. Okay. All right. So the things that I need now is the no mean, the yes mean, the no standard deviation, and the yes standard deviation, right? That's the things we need. Equals, 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 equals. Let's shift all these to the right. Alright, so equals the sum of all the no's divided by, this value here, which we don't have. We forgot to put the n, which is 32 for both of them, so we can just keep it as 32. Okay, that'll work. And then the equals the sum of the yeses divided by 32. Okay, and standard deviation dot sample of the no's and the standard deviation of the sample of the yeses. Okay, so the mean difference equals yes minus no. So about 50 is the average difference basically. So that's this value right here. Then we need our t. For the confidence interval. So I guess this would be our t alpha 2. Alpha 2. We'll put that. Okay. So 0.975. So what am I doing? T dot inverse 0.975, comma, this minus 1 is the formula. There's our t value. Let's think about why that is, because the problem said, and we read it, figure out a 95% confidence interval. Okay. So if we do this, That's 0.95, which means this is 0.025. And it's the same thing on that side, correct? So from here to here, right, to get our t-value, right, because that's the t-value we want, that's that t-value, it's 0.25 plus 0.95, so 0.75, right, which is what I used there, correct? So my alpha for the confidence interval, right, is 0.05, right? Because it's 95% confidence, basically. All right, so the next problem is I need this standard deviation right here, right? That's a problem, okay? All right, so I'm going to copy... That's not what I want. Let's go back to the notes. Copy that. Paste it. Okay. All right, so we're going to want, we already have XD, we don't have the standard error which is this piece right here. That's the standard error, right? Because if you remember correctly, for every confidence interval, right, that's the standard error. That's the critical value. And you put these together, you get the margin of error. Right? So it's basically the sample statistic plus or minus the margin of error is the confidence interval, right? Because you get the minus side and you get the plus side. The sample statistic is this, basically, this time. Okay, so let's do SD, right? Okay, so if we do this, I need to do, if you look at the formula here, it's the difference between the individual difference and the mean difference, and then square it, basically add them all up, which is that last piece I have up here, right? So it's the individual difference minus the mean difference, and I square it, okay? And you want to change, you can do this with a dollar sign, okay? So now when you drag it down, no matter which one I click on, it's going to go to that right there, right? You can, so you notice I did the difference between the S and no means, but you can also do equals the sum of all these differences, right? You take all these differences and add them up, right? And divided by the number, look like you get the same answer, right? So you can do the difference between the total means or the sum of the individuals, you get the same answer. It doesn't really matter. So either way, this is the individual difference minus the mean difference squared. So I drag this all the way down. Okay. So if we look at the formula, it's equal to the square root of the sum of all these. Okay, close parentheses, look at the formula. It's the sum of all those divided by n minus 1. I'm not going to type in n minus 1, I'm just going to type in 31, because we know it's 32. I'm not going to do the minus 1, it'll throw off the order of operations. Okay, so there's my standard deviation. So the standard error, right, is that divided by the square root of this n, right? So there's my standard error. Okay. So that's what I need right there. I need the XD, which I have. I need my t-value for confidence interval. And I need the standard error, which is right there. So now I can figure out my confidence interval. So equals the mean difference minus the t-value times the standard error. There we go. So I'm going to click that, copy it, and then paste it over there, and change that to a plus. And I believe these are in millimeters, right? Was it millimeters? I forget. Oh, it was milliseconds. I'm sorry, milliseconds. That's what it was. Let me go back. milliseconds. Is that the correct abbreviation for milliseconds? MSEC. Yeah, we got it. MSEC. I got it. We were right. Okay, so that's the confidence interval. We'll rewrite that afterwards on our paper. Let's write it down. Why not? Let's get this out of the way and put this on here. Okay, so my confidence interval is 31.07. No, it was just 70186. It's a ... obviously, is less than the mean sub d. And then I got 69.54814 ... And this is milliseconds, right? So basically we can say in context, right? Let's make this blue. Format color blue. I'll make this blue. So we are 95% confident the true difference in reaction time is in the confidence in the interval. Let me think. We are 95% confident the true difference in reaction time is in the interval, right? So 5% of the time it might be wrong, basically. Okay? Because our sample said what, basically? Our sample said 50. So 50 is obviously in there, but is that the real answer? Who knows? Might be more, might be less for the true actual. You know what I'm saying? Who knows? Okay. So now we need to do the hypothesis test, right? So we want to know if there's a difference, basically. Okay. So we got this. We need another t for the hypothesis test. We'll just put t because it's regular old t. It's not a. It's one we're going to calculate. We need the degrees of. We already have degrees of freedom, do we? No, degrees of freedom and the area. Okay, so degrees of freedom is easy. We just have to do this minus 1. Okay, and our t value is right here. So that's equal to our sample minus the population, which would be 0, divided by the standard error. Right? Because you always assume that the difference in the population is nothing. Right? That's the null hypothesis. Okay? So we got that there. So let's do our hypothesis test now. So basically, let's see. Carry out. Okay. So we'll just write the hypotheses. So if we write the hypotheses, H sub 0, H sub A. So be the population sub difference is equal to 0. That's what the null is. So the population, let's just copy this. So we're just saying there is a difference, right? If there is a difference, so we don't care if it's less than or greater than. So we're going to say not equal to, basically, right? That's our what we're doing there, correct? Okay, so let's make that blue. Format color blue, right? So the area equals, that's approximately what? Okay, so we did equals normal dot distribution. No, we're not doing normal. We're doing t dot distribution. And this, comma, degrees of freedom, comma, true. This will give us the wrong answer. Okay, let's figure out why that's the wrong answer. Okay, so our t distribution generally goes like this, right? And we have a t value up here of 5 point something, right? This t value is over here. It's a pretty high t value on the positive end. Okay, so we believe there's a difference. The problem is the difference can be here, the difference can be here, correct? So first off, to get to this end over here, I have to do 1 minus. But then I have to double it to get both ends, right? So 1 minus just gets me up to the high end. But then I also need to double it, because it's a two-tailed test. Well, how do I know it's a two-tailed test? Oof, that's pretty small. So let's change this to home, and we want numbers, and we'll increase the number of decimal places. That's close enough, right? So I know it's a two-tailed test because it's not equal to. So my area is 0. How many zeros are there? I can't. Oh, my eyes are terrible. 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5, 5, 8, dot, 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 which is my p-value, right? Okay. So essentially, my p-value is less than alpha, because my alpha is going to be 0.05. How do I know it's 0.05? Well, so the alpha for the hypothesis test is also going to be 0.05. You're like, well, they always should be the same, right? Well, no. That's if they're both two-tailed. This was a two-tailed because confidence intervals, we only do two-tailed ones. And this is a two-tailed, so it matches. If this was a one-tailed, it would have to be half that because it would only be one end of the curve that we did, basically, right? So you would have to half it if we just did one end versus the other, right? But this is a not equal to, so it's a two-tailed. So it's actually the same. Okay, so going back to my thing here, the p-value is less than alpha, which means we should reject the null hypothesis. There is enough evidence to reject the null hypothesis. The sample is significant, which means it's in the shaded region, basically. So in context, there is enough evidence to suggest there is a difference in reaction time for students when they use a cell phone while driving. Okay, we're not saying whether it's more or less. We could probably change the hypothesis test for that. Let's see here. Does the confidence interval there is none? Right, so we see here. Yeah, because you assume there is none and you prove otherwise. Okay. Does the confidence interval and the significance test come to the same conclusion? Well, is 0 in there? Well, if I look in there, is 0 in there? No, it's not, right? Which means we should have rejected it, right? Because if it was in there, we would not have rejected it, basically. So therefore, the confidence interval is coming to the same conclusion as the hypothesis test.